Chapter 1.0, Transformations Preview. This section is basically a very quick review of some of the important concepts from Math 20-1. Identify the type of function and accurately graph it. Label at least 3 significant points. The first function is y equals x. That is a linear function. We can make a table of values, x and y. When x is, let's say, -3, y is also -3 since y equals x. So x -2, y is -2. X -1, y -1. X 0, y 0. X 1, y 1. X 2, y 2. X 3, y 3. We can plot those points, so -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, and so on. And then we can join those points with a line. For this function, we have an x-intercept and a y-intercept at the origin, 0, 0. X-intercept and the y-intercept. And it says label at least 3 significant points, so we'll call that 1 point. And we could label this one here is x equals 3, y equals 3. And we could go, this one here is x is -2, y is -2. We can also graph this on our graphing calculator. Let's do a review of that. I only have a TI style calculator on my iPad, so we'll use that type. We have y equals x, so I'm just putting y1 equals x, enter, graph that. I'm going to change my window to standard, so I can go zoom standard, which in this calculator is number 3, and that gives me -10 to +10 for both axes. I could find the x-intercept, second trace number 2, enter. I have to go left bound, so left of the x-intercept, hit enter, right of the x-intercept, hit enter, and then it tells me that it's at 0, 0. On the Casios, you graph by doing menu and then choosing the graph icon. It's often number 5, depending on the model you're using. Then enter y equals x and hit F6 for draw, and then you can change your window to standard by doing F3 for V window, and then F3 again for standard, then hit EXE, EXE again, and it graphs the same image that I have on the iPad here. And then to find the x-intercept, you go F5, and then it's called the roots. Remember that x-intercepts are called roots, they're called the zeros, and they're called the solutions. So any of those 4 terms would mean the same thing. And again, it tells us that our x-intercept is at 0, 0. Next function is y equals x squared. We should definitely remember this from Math 20-1. We use this a lot. This is a quadratic. We can make a table of values, x, y. Let's go from -2, x is -2, y would be -2 squared, -2 times -2, which is +4. X is -1, -1 squared is +1. X is 0, 0 squared is 0. X is +1, then 1 squared is 1. X is +2, 2 squared is 4. X is +3, 3 squared is 9. So at -2, we go up to 4 and put a point. At -1, we go up to 1, put a point. We have a point at 0, 0. positive 1, we go up to 1. X equals positive 2, we go up to y equals 4. And then x is 3, we go up to 9, which is off this graph. Then we join the points together with a curve to make a parabola. We can graph this in our calculator. X squared graph. We have an X-intercept, which is also our Y-intercept at 0, 0. Just a reminder, X-intercept is when the graph crosses the x-axis or when it's on the x-axis. Y-intercept is when it's on the y-axis. So this point is on both the x and the y-axis, which makes it an X-intercept and a Y-intercept. And we can find the X-intercept in our calculator. Second trace for TIs, F5 for Casios, number 2 for TIs, F1 for Casios. Casios, you'll just get the answer once you do F1. TIs, you have to do left bound, right bound. So left bound, left of that point of the X-intercept, hit enter, then go right of that point, hit enter. Now, sometimes our calculators do this where it's like negative 0.02. I don't really know why it does that. It seems to be a glitch, and it seems to happen more often with this app that I have on the iPad, but it just means 0, 0. Next one, y equals x cubed. X cubed, so this is a cubic unit. We can do a table of values. We'll let x equal negative 2 to start. Then y, negative 2 to the power of 3 is negative 8. X is negative 1. Y would be negative 1. X is 0. 0 cubed is 0. X is 1. 1 cubed is 1. X is 2. 2 cubed is 8. We plot the points. Negative 2, 8. That's off of our grids. We can't graph that. Negative 1, negative 1. Negative 1 on the x, down 1 to negative 1 on the y. 0, 0. 1, 1, and then 2, 8. So that would be, let's say it's somewhere up here-ish, and negative 2, 8 would be down here-ish. So cubic functions look something like this. They curve and kind of flatten out at the X-intercept. And we can graph that. X to the power of 3 graph. And there's our graph. We have, again, a point 0, 0, which is an X-intercept, and a Y-intercept. Oh, and then we're supposed to label 3 points. So this is the point 1, 1. And this is the point negative 1, negative 1. And we can go back to our quadratic and label 2 more points that we didn't do. So let's do this one. Here is the point 2, 4. And we'll do this one is the point 1, 1. Next one, y equals square root x. The type here, what is a root called? It's called a radical. So this is a radical function. It's a square root, so can we take the square root of all numbers? No, we can't take the square root of negative numbers. So when we do our table, we would only have 0 and positives for the x value. If we did negative 1, square root of negative 1 and we get an error because that is undefined. We can't take the square root of a negative number. Then we do 0, the square root of 0 is 0. 1, square root of 1 is 1. 2, the square root of 2 is a decimal. 1.4142, ... Not very helpful for graphing. A perfect square number is 4, and the square root of 4 is 2. That's much easier to graph. So we can graph the points. We start at 0, 0, then we have a point at 1, 1, then we have a point at 4, 2. And then I join those points together, and we get a curve. We can label 3 points. We have 0, 0, which again is the X-intercept and the Y-intercept. Then we have this point here is 1, 1, and then we have 4, 2. We can graph the radical function, square root x, graph, and there we go. I can try to find my X-intercept. It might give me an error because I can't really go left bound of that point. Yeah, it gives me an error. When I do it on my Casio calculator, it calculates it fine and tells me it's 0, 0. So those of you who use TIs, maybe it'll work on a regular TI. It's just this app doesn't work. I'm not sure. Next one, we have y equals 1 over x. We did a chapter on these types of functions in 20-1. It is a fraction, and numbers that can be written in fractions are called rational numbers. So a function that is a fraction is a rational function. Let's make our table of values. If x is -3, then y is -1 over 3. If x is -2, then y is -1 over 2. If x is -1, then y is -1 over 1, which just equals -1. If x is 0, 1 divided by 0, we can't divide by 0, right? 1 divide 0 gives us an error. It's undefined. And we might remember from 20-1 that when the denominator of a rational function is 0, that creates a vertical asymptote at that x value. Then if we have x equals +1, y would equal 1 over 1, which is 1. And then x equals 2, y would equal 1/2. X equals 3, y would equal 1/3. So we have a vertical asymptote at x equals to 0, which is the y-axis. Then for negative x, we have -1, -1. Then for -2, we have x is -2, y is -1/2. And for x is -3, y is -1 over 3. We'll say that's about there. Then we join those points together with a curve, and as the curve gets closer to the vertical asymptote, it goes down. It's getting closer to the vertical asymptote, but it's never going to reach or cross the vertical asymptote. Then the other part of this graph, there's 2 parts to a linear rational function. The positive side, we have 1, 1, 2, 1/2, and 3, 1/3. And then same idea, we join the points with a curve, and as we get closer to the vertical asymptote, y approaches infinity. We can write a few points down. We have 1, 1. We have -1, 1, 1, and we need one more. We can do this one here is x equals 3, y equals 1/3. Then we can graph this. Fraction 1 over x, graph, and that's what it looks like. The graph will show the vertical asymptote, so it kind of looks like it's all connected, but it's not. That's just the vertical asymptote. These two portions, the two curves, that's the graph, and they are not connected. They are separated by the vertical asymptote. So because the vertical asymptote is at the y-axis, we won't have a y-intercept. And also, rational functions have a horizontal asymptote. The base rational function y equals 1 over x, the horizontal asymptote is at the x-axis, so we will not have an x-intercept either. Next one, y equals absolute value of x. This is an absolute value function. You can make a table of values, x, y. We'll start with -3. The absolute value of -3 is asking what is the distance that -3 is away from 0. Distance is positive, so it is 3. So the absolute value is always a positive number. Absolute value of -2, how far is -2 away from 0? It's 2 units. Absolute value of -1, how far is -1 away from 0? 1 unit. Absolute value of 0, how far is 0 away from 0? 0 units. Absolute value of 1, how far is 1 away from 0? 1 unit. Absolute value of 2, how far is 2 away from 0? 2 units. And absolute value of 3, how far is 3 away from 0? 3 units. We plot our points, -3 and y is +3, x is -2, y is +2, x is -1, y is +1, x is 0, y is 0, x is 1, y is 1, x is 2, y is 2, x is 3, y is 3. So we get a V shape for an absolute value function. We have 0, 0, which again is the x-intercept and the y-intercept. And pick some other points. We have x is 3, y is 3, and over here we have -2 and 2. We can graph this. To get absolute value in a TI, you go math over to num, and then it's the first one, number 1, and then you put absolute value of x. To get absolute value on a Casio, you push option, F5 for num, and then F1 for absolute value. Enter x in your absolute value, and then graph, and we get the same image. We can calculate the x-intercept, left bound on the TI, right bound on the TI, and it's at 0, 0. While editing this page, I noticed a couple errors. In the quadratic function, I wrote this point down as 2, 4. That's supposed to be -2, 4. And then with the rational function, similar problem, I wrote this point down as -1, +1. It's supposed to be -1, -1. A relation is a set of ordered pairs. A function is a relation that for every x value, there is only one y value, which means it'll pass the vertical line test. Domain is the set of all possible x values, and the range is the set of all possible y values. Use your calculator to graph the following relations and state the domain and range. Sketch the relation on the graph provided. Don't forget to choose appropriate windows. Is the relation a function? How can you tell by looking at the graph? Y equals 2x plus 3, we can graph that with our calculator, but we should also be able to graph that without using a calculator. It's in y equals mx plus b form, where m is the slope and b is the y-intercept. So y-intercept at positive 3, 1, 2, 3 right there, and a slope of 2, which is 2 over 1. So rise 2, run of 1, rise of 2, run of 1, rise of 2, run of 1. If we want to go down, down to left 1, down to left 1, down to left 1. And then I can join those points with a line. And there is y equals 2x plus 3. We can also graph it on our calculator. So our grids are all 10 by 10. Our window should still be set to 10 by 10 from the last page. 2x plus 3. So then it says we want the domain, the range, and is this a function? Domain is the horizontal, the x values. So horizontally, how far left does this go and how far right does it go? We have arrows. It's going on forever, so it's going to continue going down and left forever and up and right forever. So in terms of left, right, it's going forever left and forever right. The easiest way to write that, and the most common way, set notation, x such that, we always start set notation this way. And then if it's just everything, negative infinity to positive infinity, we can write that as x is an element of the real numbers, and then close our bracket. The range is the vertical, so how far down and how far up does this relation go? It's going to go forever down and forever upward. So again, will be all real numbers, or from negative infinity to positive infinity. Curly bracket y such that y is an element of the real numbers. Is this relation a function? Looking at a graph, we can tell if a relation is a function by seeing if it passed the vertical line test. If we take a vertical line and we put it anywhere along that graph and it only touches one spot at a time, then it is a function. So this one passes the vertical line test, so yes, it is a function. And we also wanted to find the x-intercept and the y-intercept. Second trace number 2 for the x-intercept. Left of the x-intercept, hit enter. Right of the x-intercept, hit enter. And it tells us that the x-intercept is negative 1.5. So this point here is negative 1.5 and y is 0. And our y-intercept we already know is 0, 3, because we got that from the equation, but we could do that graphically as well. So for a TI, second trace, and then number 1, it says x equals, and you can put in any value for x. So at the y-intercept, we know that x is 0. So we put 0 and hit enter. For Casios, you do F5 and then F4. It says Y ICPT, y-intercept, and it just tells you it's 0, 3. B, y equals negative x squared plus 2. Go back to our y equals, clear this, negative x squared plus 2. Graph. We can find some values to help us graph this. Remember, quadratics have a max or a min. In this case, we have a max point because it's like a hill or a mountain. So second trace, we want to find the maximum, number 4. We have to go left of the maximum, hit enter, right of the maximum, hit enter, and then it tells us the maximum is at 0, 2. For Casios, you just push F5, and then it is F2 is max. Next, let's find the X-Intercepts. Second trace number 2. Left of, there's 2 X-Intercepts, so I have one here and one here. So I'm going to focus on this one first. Left of that point would be here. Hit enter. Right of that point would be here. Hit enter and hit enter again. And it says negative 1.414. So I can approximate that to be about there. And then repeat that process for the second one. With the Casios, once you found the first one, you just use the cursor to go left or right and it'll tell you the second one. Left bound of this X-intercept would be above it, hit enter. Right bound would be below it, hit enter. And positive 1.414, so about here. Then join the points to make a parabola. The domain, we have arrows. We're continuing to get wider and wider and wider. So it's going to go forever left and forever right, which means our domain is X such that XER. Our range for quadratics is defined by the max or min. In this case, we have a max, so Y such that all the Y values are going to be at or below the maximum. So the maximum is 2, Y is less than or equal to 2, and then we have to state that Y also has to be real numbers. So all real numbers that are less than or equal to 2. Is this a function? Does it pass the vertical line test? Touches once, touches once, touches once. Yes, anywhere we go, it's just going to touch one time. So yes, this is a function. And let's just label our X and Y intercepts. So Y-intercept was at 0, 2. Our X-intercepts were at 1.4140 and negative 1.4140. Y equals absolute value of X plus 4. Go back to Y equals, clear. Absolute value, we do math, num, number 1. For Casios, you do option, go to num, and then it's F1. So absolute value of X plus 4. Graph that, and this is what we get. We have a minimum value, we can find that. Second trace number 3 for minimum. Left bound, enter, right bound, enter, and it's at negative 4. It says negative 4.005, it's just negative 4. X is negative 4 and Y is 0. And I can find the Y-intercept as well. Second trace number 1, put in 0 for X, hit enter, and it's at positive 4. And absolute value functions are symmetrical, just like quadratics. So since I have a point that is 4 right and 4 up from the minimum, I would also have a point that is 4 left and 4 up from the minimum. Then I can join the points. I can label my X-intercept negative 4, 0, my Y-intercept 0, 4. The domain, we're continuing forever up and left and also forever up and right. So our domain again is XER, X such that XER. The range, we have a minimum value right here at Y equals 0. So all of the Y values are going to be at or above that. y such that y is greater than or equal to the minimum, which is 0. And then y is an element of the real numbers. So all real numbers greater than or equal to 0. Is this a function? Using the vertical line test. Yes, anywhere we move that vertical line, it's only going to touch one spot at a time on the relation. That makes the relation a function. Example, find the domain and range for each of the graphs below. First one is an oval. The domain from left to right, what is the farthest left that our graph goes to, would be here at -6. What is the farthest right? That would be this point at 8. Then our domain is x such that -6 is less than or equal to x is less than or equal to +8, and x is an element of the real numbers. The range, what is the lowest and highest the graph goes, is -5 and 3. Y such that -5 is less than or equal to y is less than or equal to 3. Y, E, R. Close the bracket. Is this relation a function? If I use the vertical line test, I can see right away that I touched 2 points at the same time with my vertical line. So no, this is not a function. Next one, domain from left to right. What is the farthest left our graph goes? That would be this point here, which is at x equals 3. What is the farthest right it goes? Well, it's continuing to get wider, even though it looks like it's slowly getting wider, but it is getting wider forever and ever. So it's going to continue on to +infinity. Then we have x such that smallest x value is 3 is less than or equal to x. And then for infinity, we never equal infinity, so we just say is less than infinity. And then x is an element of the real numbers. Close the bracket. Range, what is the lowest the graph goes? Well, it's continuing to go down forever, so that's -infinity. And what's the highest it goes? That would be at this point, which is at y equals 5. Then range is y such that -infinity is less than, not equals to, not less than equals to, because we can't equal infinity. So just less than y, which is less than or equal to 5, and y, E, R. Is this relation a function? Does it pass the vertical line test? Yes, because this is continuing to get wider. It's only going to touch at one spot at a time, so yes, this is a function. Let's also look at interval notation for domain and range. Interval notation is where we use square or round brackets. Square brackets mean that value is included, so when we use the less than or equal to symbol, that's when we would have a square bracket. A round bracket means it's not included. So this last example, we could write it in interval notation. The 3 is included, so it's square bracket 3, comma, infinity, and then infinity is not included, so round bracket. So you have brackets, your lowest value, comma, your highest value, and then which bracket you use depends on if the value is included or not included. So the range would be -infinity, comma, 5. -infinity, we can't actually equal -infinity, so round bracket always for infinity. Square bracket for the 5, because that is included. We are going to have a value that actually equals 5. -6 to 8. -6, comma, 8. They're both included. They both have the less than equal to symbol. There's no holes in the graph at those points, so square brackets for both. The range in interval notation, -5 to 3. And again, they're both included, so square brackets for both. Let's do these ones as well. XER, if you want to show everything, that would be negative infinity to infinity, and we use round brackets for infinities. Range would be the same, negative infinity to infinity, round brackets for both. This one again, negative infinity to infinity, round brackets. Then y is less than or equal to 2. That means it's going from negative infinity up to 2, round bracket for infinity, square bracket for the 2, because 2 is a value for y. And last one, negative infinity to infinity for XER, round brackets for both. Y is greater than or equal to 0, so 0 is the smallest value. Infinity would be the largest value, round bracket for infinity, square bracket for 0. Set notation is used more often, but you do also have to know interval notation. Quadratic review. A quadratic function is a function of degree 2. It can be written in two forms. The general form is y equals ax squared plus bx plus c, which is the form we use when we factor a quadratic or when we use the quadratic formula. The standard or vertex form is y equals a bracket x minus h close bracket squared plus k. This is the form that we convert it to when we complete the square on the general form. We use this form to algebraically solve for the vertex of the quadratic. Recall from Math 20-1, if a is positive in either of these forms, the graph opens up. If a is negative, the graph opens down. If h is positive in the vertex form, the graph moves right. And if h is negative in the vertex form, the graph moves left. If k is positive in the vertex form, the graph moves up. And if k is negative in the vertex form, the graph moves down. Example, graph y equals x plus 1 squared minus 4. Find the following: the direction of opening, the vertex, which is the max or min, the axis of symmetry, the domain, the range, and the intercepts. So vertex form is y equals a x minus h squared plus k. We have y equals, there's nothing in front of the brackets, which means a is positive 1. Then we have x plus, whereas the standard form has x minus h, so we can write that as x minus negative 1, close bracket squared, and then we have minus 4. So a is 1, h would be negative 1, and k would be negative 4. A, direction of opening, the a value in the function is positive, so it opens up. B, we want the vertex. The vertex is hk. Which in this case is negative 1, negative 4. We can plot that point. Negative 1, negative 4 is right there. Part C, the axis of symmetry. We should recall from Math 20-1, the axis of symmetry is the x value of the vertex. So x equals negative 1 in this case, and that is the line across which the graph is symmetrical. So if I draw a line, our axis of symmetry is x equals -1. Before I do my domain and range, I'm going to graph this function. So it would help if I had the intercepts. I'm going to do that next. For the y-intercept, you let x equal to 0 and solve for y. And then we have y equals bracket 0 plus 1 close bracket squared minus 4. 0 plus 1 is 1, 1 squared is 1, so we have y equals 1 minus 4, which gives us y equals -3, which means we have a point at x equals 0, y equals -3. That is 1 right and 1 up from the vertex. Then this is our line of symmetry through the vertex, so that means we have a point that's 1 left and 1 up from the vertex as well. Mark our y-intercept. And our vertex. And then to find the x-intercepts, we let y equals 0 and solve for x. Then we have 0 equals x plus 1 squared minus 4. We add 4 to both sides. We get 4 equals bracket x plus 1 close bracket squared. We square root both sides, but because x plus 1, we don't know if that started as a positive or a negative before it was squared, we have to do plus minus square root. So plus minus square root 4 equals x plus 1. The square root of 4 is 2, so plus minus 2 equals x plus 1, and then subtract 1. We get plus minus 2 minus 1 equals x, which gives us two different cases. One where we do 2 minus 1, which equals 1, and one where we do -2 minus 1, which equals -3. So those are our two x-intercepts at x equals -3 and at x equals 1. And then I can draw my parabola. Now that I have my parabola drawn, I can do my domain. We're continuing forever, getting wider in both directions. So XER, and for quadratics, domain is always XER unless it's a word problem. X such that XER. E, the range. Range for quadratics is defined by the maximum or minimum. In this case, we have a minimum at y equals -4. So all y values are greater than or equal to -4. -4 is less than or equal to y, and YER. And then F, our intercepts, we did that. Our y-intercept is at -3, and our x-intercepts are at -3 and +1. We have 2. And let's mark the x-intercepts as well. This was 1, 0, which is an x-intercept. And this one here is -3, 0, also an x-intercept. Let's review completing the square. To convert a quadratic function from general form to standard or vertex form, we must complete the square. We have y equals 3x squared minus 18x plus 26. First step is we want to group together the x terms in brackets. We want to leave a space and then put plus 26, our constant term, outside the brackets. The next step is to factor out whatever's in front of x squared. Even if it's not common to both of these, whatever is in front of x squared, you want to factor it out so that you can have 1x squared in the brackets. So we're going to factor out 3. We get y equals 3 bracket x squared. Negative 18x divided by 3 is negative 6x. Close the brackets, and then we still have plus 26. That is not affected by factoring out the 3, just the brackets. Step 3, we want to look at the middle term. We want to divide that by 2 and then square it. So negative 6 divided by 2 is negative 3. Negative 3 squared is 9. Step 4, we're going to take the number from step 3 and put it into our equation. We have x squared minus 6x. We're going to add the number from step 3 inside at the end of the brackets. And then we're going to subtract that number outside the brackets, but also times it by whatever we factored out of the brackets. So that's 3. So we add inside and subtract outside. And the reason we have to multiply the negative 9 times 3 here is because when we add 9 here, we're really adding 3 times 9. So we have to subtract 3 times 9 so that we're not changing the equation. If we add 27, which is 3 times 9, we subtract 27, which is 3 times 9, then really we're not changing the equation. So we must multiply by the number in front of the trinomial to keep the function the same. For step 5, we're going to factor this trinomial. The way that we created that trinomial, by dividing the middle term by 2 and then squaring it, and then adding that value inside the brackets, that creates a perfect square trinomial. A perfect square trinomial factors to a binomial squared. The first term of the binomial is the square root of the first term of the trinomial, so square root of x squared is x. The last term in the binomial is the square root of the last term in the trinomial, which is 9, so square root of 9 is 3. Then the sign for the binomial comes from the sign of the middle term of the trinomial, so a negative, negative. The binomial is squared, and then we have our constants outside, so plus 26, and negative 9 times 3 is minus 27. And then step 6, we simplify our constant terms. We have y equals 3 bracket x minus 3 squared. 26 minus 27 is negative 1. The standard form, or the vertex form, of this quadratic is y equals 3 bracket x minus 3 squared minus 1. And then from there we could tell that our vertex would be h, which is the opposite sign of this, and k, which is that. So positive 3, negative 1. The whole point of putting a quadratic in vertex form is so that we can algebraically determine the vertex of the quadratic. Next one, y equals 5x squared plus 30x plus 41. Step 1, group your x terms together. 5x squared plus 30x space bracket plus 41. Step 2, make that x squared term have a coefficient of 1, so factor out 5 in this case. 5 and then bracket x squared plus 6x plus 41 outside the brackets. Step 3, we want to take the middle term, divide it by 2 and square it. We get 3 squared, which is 9 again. That was step 3. Step 4, we want to take that value from step 3 and add it inside the brackets. And then we have our constant 41 outside, and then subtract that value from step 3 outside and multiply it by the number in front of your brackets. Step 5, we can factor the trinomial down to a binomial squared. Square root of x squared is x. Square root of 9 is 3. The middle term is positive, so it's a plus 3. Then that binomial is squared. Then we have plus 41 minus 9 times 5 is 45. And finally, simplify the constant terms. Y equals 5 bracket x plus 3 squared. 41 minus 45 is negative 4. And then from this, we can tell that our vertex would be, the h value would be negative 3, since it says x plus 3 here, h is negative 3, and then the k is negative 4. That brings us to the end of Chapter 1, Lesson 1.